The challenge is that because everything is computed iteratively, we can't predict where the simulation will end up. So we can't really prepare for the simulation to end at the same point where it started. And we have to synchronize both of the terrains so that it ends at the same part of a chunk where it started, and all the instances need to look the same, and the character needs to end in the same pose as the one it started with. So for that, my solution is to define a fixed number of frames at the end of our animation on which we are going to override the computing system for the position and for the animation of the character, so that for the whole duration of this end transition, we can have a more predictable behavior for the evolution of everything and make sure everything lines up. This, of course, will not be perfect, and the fit of the character might be sliding and everything, but it's the only way I've found to make it easily loop and have this nice simulation. So let's start with the sweep time for our character, because it will be easier. First, let's add some geometry nodes inputs. First, I want the total frame count, which will be an integer, and in my case, it's 500 frames. Then we want the transition length. So let's say I want to start the transition 80 frames from the end of the animation. In order to detect when we will be in our transition zone, we need the scene time, and we need to compare the frame for this one with some value that will compute with a greater than or equal node. So we'll be in our transition zone when the current frame will be at or above the frame count minus the transition length. Now this will allow us to switch between values, so we can drive this into a switch node set to float, and we can put this before our stored named attribute node. So when we are not in the transition node, we have the value as before, and when we are in the transition zone, we'll override this. During the transition, the animation factor will be evolving linearly, so we can use a map range node to do that, and we will be mapping the current frame, which will be evolving from the frame count minus the transition length to the frame count plus 1. We are adding 1 here, so that the end frame of our animation will be just before the first frame of the animation, making everything loop without repeating frames. Now this output will start at 0 and reach its final value, which we'll be computing later, but this we will add to the animation factor on the true branch of the switch, like this. To override the animation cycle, we need to know first at what point we are in the current animation cycle at the start of the transition zone. This will allow us to know how many frames we would need to complete this animation cycle. With this, we will know how many frames we have left in our whole animations, and then we will be able to compute how many cycles of animation we can fit into the final frames of the animations. So first, let's set the typical length of an animation cycle with the value node. Here I am setting it to the length of the middlemost animation, which is the run normal animation, and its length is 26 frames. To know how far along we are in this animation, I can take the animation factor, modulo 1, and take this value and compute 1 minus this. If we multiply this with the typical length of our animation, we will get how many frames we need to finalize this animation loop. And so in order to know how many frames we are left at the end of the animation to fit it a certain number of cycles, we need to take the transition length. We need to subtract this frame value from the transition length. So this gives us the exact number of frames until the end of the animation in which we have to fit a certain number of full animation cycles. So to know how many animation cycles we can fit, we can divide this by the length of our animation. This value may be a float value, but I want to know about how many full cycles of animation I can fit, so I can run this value. And now I need to add back the proportion of the current animation which is left, which is the value from this node. And this will be equal to the number of cycles we have to fit in the rest of our animation. So this we can plug into the map range node as the max value. Before testing this, we need to fix the animation factor from the simulation zone so that it does not continue to evolve when we are in the transition zone. To do that, we can just add a switch node set to float into our simulation zone, which we are going to put on the next anim factor line, and this will allow us to switch between the previous value or the value we computed before, making sure that if this switch is enabled, the animation factor will never be updated with a new value. And now the setup is ready to test. So let's bake the strip time and run our animate strip time script. And when everything has been run, to test if it's been working correctly, we can't just use the character, because at the moment it is still blending between the different animations based on the terrain, and it might not be on the same animation at the beginning and the end. But if we are hiding its collection, showing our animation library collection, here we can see for any of the meshes that everything is looping correctly. Now we just need to override the terrain so it is looking the same at the start and the end. So for that, the principle will be the same. We need to set a certain transition duration, fix the values that are evolving from frame to frame beyond this point, and make the movement of the terrain evolve linearly, while also blending it with the noise value from the beginning of the terrain. First, so we can compute and check everything more quickly, I will just add a switch node in order to avoid the setup of all the instances, which are making everything a bit heavy. First, we need to know the travel distance. So on the simulation zone, add the new input, float, and distance. So this will be like the chunk offset, like this. Now, just like the strip time, we need to know when we are in the transition zone. So we need to compare the scene time frame greater than or equal, and we need new parameters on the input, which are frame count and transition length. Set to 580, subtract, and let's put this into the compare node. Now we will also need another one, set to integer and equal. So just like the strip time where we set a target frame count, here we want to target a transition speed, which I'm going to set to 3 meters per second. And with this we can compute the transition length we want to go over during the transition. For that, we need to multiply the delta time with transition length, which will give us the duration of the transition, and by multiplying this with our target speed, we get the target distance. Now we need to fix this target transition distance to a fixed number of chunks, so we need to divide this by the chunk size, then we can round the value and multiply it back by the chunk size. From this, we need to remove the current distance we made in a chunk, which we can get with the distance attribute we created before, modulo the chunk size. So this is the final transition distance, from which we can compute the final transition speed by dividing this by the transition length plus 2. So the last frame isn't the same as the first frame, and then you can divide this again by the delta time of the simulation. Now this is the final transition speed, which we need to replace the computed speed from the state value blend. So here we can add a switch node, set to float, and for the boolean we'll get the result for the compare operation with the greater than node, and for the true value we can add a new input to the simulation state, which will be the transition speed. Now this one will always stay the same, so we can plug in this from the input to the output, except when we reach the beginning of the transition zone. So this is where we use the output from the equal test, and when we get in this, to replace this with the final transition speed, just like that. And now the output of this can go into the true state of the switch node, which overrides the speed from before. Now let's test this. And this seems to work great, as the final position is about the same as the start position. We can see this more clearly if we unplugged the Z deformation and bake this again, and now the animation should be pretty seamless. Perfect. Now we need to blend the deformation of the terrain near the end so it matches the deformation at the beginning. For that, we need to know the distance at which we will reach the end. So the first step is to compute the final Y offset, so we can add another input to the simulation zone, which is going to be a float named final Y offset. You can just set a very big value you are sure you will never reach, 1 million. We can also plug this from the input to the output, and in between you can also set a switch node plugged with the same boolean like this. And to compute the final chunk offset, we just need to get the final transition distance, to which we are going to add the distance from here. So those values should be the same, like this. And this is the final chunk offset. Now we can plug this into the new switch node, just like this, and we can test if it works well by comparing the position, which is the attribute right here. So let's separate the coordinates and compare the y position with a greater than value to this final offset value. So let's display this and bake everything. So with this comparison, we can test that we can correctly predict the distance at which we will finish the animation, which is precisely at the middle of a chunk. And now we'll be able to use a map range to make a blend between the value of the noise computed like before and the noise used at the beginning of the animation. So from this y coordinate, which we separated, we can plug in a map range node. As we want to end with the same noise value as the beginning, we want the three chunks here to have the same noise value. So we want the transition to end about here. So the end of the transition will be the final y offset minus the chunk size. And let's say that for the value before, we want the same value, but minus 2 times the chunk size. So now like this, we have a transition zone, which will smoothly blend between the normal computed value of the noise in black and everything in white will fade in to the noise value that we have at the start of the animation, which will look like this. So now to blend between the value of the noise at the end and the beginning, we unfortunately can just blend between the different position value, because this will otherwise also sample value anywhere in between the start and end position. So we need to duplicate all this noise computing with Ctrl-Shift-D and blend between different offsetted values of this. So let's make a bit of room for this. Move our three noises a bit down, and here we can add a mix node set to float to mix between the normally computed value of the noise and a one-wheel offset by adding a vector math node to which we will subtract the final distance set on the y-axis. Now with the factor input of the mix node is the output of our map range node from before. The final distance value I used is the one from inside of the simulation, because otherwise it will create a dependency loop. And with this setup, the final position of our simulation is matching with the first position of everything. And in this case we are lucky, because the general the offset we are matching, but if one noise has a really low value and the other have a really high value, we'll have a very high slope between them. So we need to account for that. So we need to compute 2 more noise values. So let's duplicate this 2 more times. And for the inputs, let's put some combined XYZ node. Now one noise value will be the noise at the start on this point, so with an offset of minus the chunk length on the y-axis, and the other will be the noise value for the end, so with the final distance minus the chunk size. And this is basically a global v offset for the noise at the beginning of the animation, and this is at the end. So to the noise we computed before, we need to subtract the value from the beginning and add back the noise value at the end. So we can plug this back into the mix node and test this out. And now the terrain looping is pretty seamless. Now one important thing to note here is that it is only starting to compute when you are in the transition zone. So if the transition isn't long enough, we might have some zones that are jumping. But it is important to check that when the values are jumping, for example like here, it is way outside of our island, so the effect won't be seen. Now let's tidy this mess up a bit. And now let's see how it looks with the first instances. So I'm going to remove my override, and just for now I will mute the tree farming because it's quite expensive. So the first thing we can see is that the biome isn't the same at the start and the end. So we'll need to override this and make sure that we apply a single biome on the first and last chunk. To do that, we can get our named attribute fake position, separate XYZ, and on the Y input we can add two map range nodes. The first will go from the chunk size to the chunk size multiplied by 2. So everything in black here will override the chunk to be the chunk of index 0. And with the second map range node, we need to do the same, but for the end. So here we will take the final Y offset as a from max value, to which we will subtract the chunk size, and for the other we'll subtract 2 times the chunk size. Now we just need to invert the 2 min and 2 max, and with this simple setup we have a black zone at the start and the end. We just need to multiply those two values together, so here it's black at the start and the end. With this blend value to switch between the original chunk index and the overridden 0 index, we can plug this into a greater than compare operation with a threshold coming from random value, so we have a hard limit, and this can be used to switch between integer, which are going to be the overridden 0 index in black, and in white the named attribute of the original biome. As you can see here, the biomes has been overridden for the start and the end, but we have an issue with the bridge, because here we are checking the values with the blend, and the bridge biome affects a whole chunk at once. So for that we need to do an override on the bridge biome selection right here, in which we also need to make sure that the first 3 chunks aren't a bridge. So we can take the chunk index and make sure the index is greater than 2. And we also need to compute the final chunk index to make sure it is not affecting the last chunks. So for that we can take the final Y offset, divide it by the chunk size from the group input, and if we check this with an operation greater than to the chunk index, as you can see here, the last 3 chunks are black. So now we can add those 2 new conditions to the bridge selection with the AND operation like this. Now the last issue we have is that the rotation and scale and every random aspect of the simulation aren't matching at the start and the end of the simulation. So we are going to override their seeds to make sure everything is the same. To do this, we need to have a new attribute which is going to store the original index of each point before they are instanced on the different chunks. So right here, before the instance of the post node, we can add a store name attribute. Let's call it source index, which is going to be an integer, and it takes in the index. Now into our instance first, we can go in, and for the ID of the random value, we can get a named attribute, which is the source index. And we can do the same for all the random value nodes. Now let's test this. And now everything is matching from the start to the end of the simulation. So the looping is really seamless now. Now let's adjust the speed at the start. For that we can set the initial value of the state and angle. In my case, because the slope is slightly downward, I can set the second state and an angle of around 5 degrees. So let's just set this one, the mask node, 2 radians, and let's put 5 degrees. Now let's bake this along with our strip time, and let's also run the script. And the animation is now really seamless. I'm just going to activate back my tree instancer, and to increase the viewport performances, I will just add a delete geometry node with a random value set to boolean, some probability, so you can delete about half of the instances, and we can switch this on and off with an is viewport test. Everything should be running a bit smoother. And that's it for this part. Hope you learned something here. In the next and final part of this series, we will focus on baking some geometry node data to a MIDI file in order to extract some audio from the footstep of the character, and finalizing this animation with compositing and sound design. Feel free to reach out to me if you have any question. Thank you for watching and see you next time.